Hi folks, welcome to Open Analysis Live. We're back. So, sorry for the delay, just Sean and I have been traveling for work and it's been crazy, so I haven't had a chance to get one of these out, even though I wanted to make this video right after I made the last REvil unpacking video, or Sodi no Kibi unpacking video. So in this tutorial, what we're going to do is we're going to talk about how to actually reverse engineer the dynamic imports for that sample, for that ransomware. So if you haven't seen the first part of this, go check out our previous video where we actually unpack this ransomware. I'll link it in the description of the video below. And then this video, we're actually going to talk about some real reverse engineering here. So no more unpacking. We're going to actually be reverse engineering how they do the dynamic imports and building a little script to do it all in IDA. And with that, let's just jump into it.
Let's just jump into it.
So, like I said, we unpacked this sample previously, and I've loaded up here in IDA. Now, one thing about this is you'll notice there's no imports here at all. So this is actually really common for malware. Once you unpack it, it might not have any imports, and this is usually because the imports will be resolved dynamically. Now, in our last video, I showed you a trick to do this dynamically. So in the debugger, I showed you sort of a hacky way to get all the imports to be resolved dynamically, and then you can kind of copy them over into IDA. And I saw a lot of comments you guys were asking, well, how would you do it if you just had to do it statically in IDA? Because I referenced the fact that that's usually how I would do it. So today is going to be all about IDA, how to actually go through step by step. Ooh, baby. And reverse engineer the dynamic strings functions and recreate them in Python so that we can actually build some imports automatically for the sample. So here we start out. You can see there's two functions here, and I'm going to show you a trick. Let's take a look at the first function. You can see here is a call that's resolved to an actual offset in the PE, but here we have a call to a D word and it's not resolved. And if we go check it out here, we can see that it actually points to just a D word. So this is not referenced anywhere in the PE file. Now here's the first tip that there's dynamic imports. Anytime you see something like that, where there's a call, but it's to a D word, not to any reference inside the PE file, that's probably an import placeholder. And there's probably going to be an import address written in there dynamically at runtime. Now, not all samples will have a placeholder. Some samples, it'll just be null bytes. In this case, they do it a little bit differently, and I'm going to be showing you guys how we figure that out. But right now, all you have to know is that this is definitely not a function. This is definitely just a D word, and it's random for all we know. The other thing, though, that sticks out here is we see all kinds of calls to these D words all in a big row here, kind of like a table, right? So this actually gives us a little hint, and for those of you who are doing a lot of malware reverse engineering, you'll definitely see this sort of thing and know, okay, well, this is probably a dynamic import table. But if you didn't know that, the tip off here is that you have a call to a D word, so you know that this is not going to work. If you were to run this in a debugger, it's not going to work. Something has to happen before you get to this point in the program in order for that to be resolved to something. And here's the sort of reverse engineering component to it. We can see that this is actually the third call. So if you remember, we started out at our start here. So this is the very first call in our program. This is the second call, and this is the third call. So we know that it's actually the second call has to have something in there where they resolve these imports. Otherwise, the program would crash when it gets here. So let's take a look at this. We'll rename it. I'll just press the N key to rename it, and I'll call it MW. I like to use MW in the beginning of all of my functions just to set them aside from other functions that are not related to the malware code. MW stands for malware. And this actually helps a lot if you're doing some diffing, because in bindiff you can actually just sort by MW underscore, and that'll actually show all of your functions that you've actually named instead of names that have been assigned by IDA. So then you can easily copy the functions over in bindiff. That's kind of a trick for a little bit more advanced reverse engineering. Probably talk about that later on in a video, but for those of you who are using bindiff, this is kind of a nice trick. So we'll call this maybe resolve, maybe IAT resolve. Again, I don't really know what it does, so I use the maybe keyword in there for anything that I'm not sure what it does, but I'm just guessing because, again, it has to have done something to replace this D word with something that's actually not going to crash the program before we get there. So let's pop into it. There's a jump here, and we get to this function, and so we have here is our prologue, so they're just function prologue, and then the first thing they do here is this kind of interesting thing here. Now you see here's a D word that's being pushed as an argument for this call. Then the return from this argument, which is always in EAX, is actually being copied back into that D word address. Now, obviously, like we saw a second ago, you have this table with a bunch of placeholders or a bunch of values, and they are eventually going to be called as functions. This looks pretty good to us. So if we just double click on this, hey, it's our table. So we've actually almost immediately found where they're resolving the imports. Now what we have to do is figure out how the heck they're doing this. So let's pop back here. We're going to name this, I just N key again, just to name it as malware underscore import address table build. And let's go back and we'll fix our other call here. So this is no longer maybe, this is definitely the malware underscore jump to import address table build. So one thing about this video is it is definitely going to be a bit longer and more in depth than our normal unpacking videos, because we are going to actually be reverse engineering this. So you're going to see kind of step by step how I do it. Hopefully it's not too boring. Again, a lot of you have asked for this type of content, so I hope it's interesting. But there is going to be a lot more sort of slow typing and relabeling and stuff, because I really want to show you how I actually reverse engineer it, so you can see sort of, you know, through my eyes how I would approach this. So let's pop in here. This is probably our table, so we're going to name this dword underscore pointer to the import address table, and this is probably going to be our import address table resolver, because again, what you're doing is you're pushing a pointer to the beginning of that table onto the stack, then you're calling this function, and then you're taking the return address from that function and you're copying it back into the table. So the only thing that this could really be doing is resolving those imports. So we can probably name that as well, malware underscore name resolver. So import address table name resolve, I guess. I'm not really sure. You know, it's just resolving the names. So now this makes me think about a technique that is super common in malware, which is where they use, instead of the import address table name, the name of the function, so like create process internal W, they actually create a hash of that function. And then they search through memory, and I'm going to show you this because that's actually what's happening here. They search through the loaded libraries for the DLLs that contain these functions for all of the names in the export table. They hash them, and then they compare them against the hashes that are hard-coded in the binary in order to locate the function that they need. Wouldn't expect you to know this if you are pretty new to reverse engineering malware, but this is such a common technique. It's been talked about to death. So anytime I see something like this, where I see a bunch of hashes that are being passed to a function, the return from that is being called as a function, you know, my mind kind of almost automatically goes to, it's probably an import that's being resolved as a hash. So anyway, so that's what I'm looking for. But if you didn't know that, again, this is kind of a tip off, the fact that you're passing in a value to a function, the return from that is actually being overwritten from that value, and then you know that those values later on in the program are being called as functions. That's what you look for if you're looking for dynamic import address tables. So let's take a look at this function. It's probably going to be interesting here. Now, here's where we get into some actual reverse engineering. So we can see this is a very large function. Looks like there's a big case statement or switch statement. And when I'm reversing stuff like this, I definitely like to use the hexphrase decompiler. So I'm going to F5 into the decompiler and show you some C code. I think I mentioned this before on this channel. I know that these tools are not available to everyone. They're quite expensive, but if you're going to be doing this professionally, it's pretty much mandatory that you have a decompiler. Again, I also mentioned that I will not be doing anything with GIDRA or GHydra. It's not the industry standard, and it just doesn't seem like it has enough support yet to waste any time on it, if that makes sense to you. I'm already like super comfortable with IDA, and that is the industry standard. If you're working in this industry, all scripts and tooling are written for IDA, so I'm going to stick with that for now. But if you want to follow along from home and you don't have the hexphrase decompiler, which is very expensive, you don't have IDA, you can actually do all of this stuff that I'm showing you, the same exact steps, just not the same commands because the interface is different, but the exact same steps. The approach to reverse engineering is identical, right? When it's just a tool, you're just swapping out the tool. I know there's some subscribers on the channel who like GITHUB or GITHUB. See you guys in the comments. If you remake this video using GITHUB, then I will definitely link it. Let me know, and I will link it so that people can follow along in that tool as well. But for now, we're going to be using Hexarray's IDA and the Hexarray's decompiler. So you can see here, we've decompiled it, and it looks like a lot easier to see what's going on here. So you see a bunch of if statements. We know that this is our argument here. I'm going to end for name, argument hash, or we'll probably call it API hash. And so we know that's what it is. So let's see where it's being used. So here's something interesting. Before they use that hash in the function, they use it here as well. They do some sort of transform on it with some XORs, assign it to var1, which is used, and then they shift it and assign it to var2, which is used in this big statement here. Okay, so what I think might be going on here is they are splitting this hash value up into two different values. So let's just follow this through the program here. The reason why I'm thinking that is because I see this big shift right. So it looks like they're doing some work on the hash here. So let's call this, we'll rename this as var underscore API hash transform 1, and this as transform 2. So it looks like they're first they XOR it, they shift left 16 and do another XOR, and then they take the result of that and they shift it right 21, and that it looks like that final value is used in this big if statement here, where it looks like they're trying to figure out which one of these functions they should call. Yeah, so it looks like they're doing a bit of math on that hash value, and depending on what it falls into, what category it falls into, then they call one of these different functions. So let's rename these functions. Yeah, let's just try and rename them quickly. I'm not sure what they're doing, but we'll just rename them so that we can keep them separate here. So again, this is something that I like to do. I like to label things to differentiate them, because I don't like to have to tell them apart based on the hex value in the subject. So I'm going to name them malware import address table fn1, and I'll just call this fn2. Okay, and then we're out of the if statement, right? Yes, that's the final of it. Okay, cool. And so we can sort of figure out what those are doing, but I did see when I clicked on this first transform that it was actually used down here. Okay, so I spotted something and I want to show it to you guys. Okay, so remember I said I think that they might be splitting these up and using the hash in two different ways. So here you have transform 2, which is used in this big if statement, used to assign one of these functions to this variable v8, and then they call v8 down here, assign the value to v13, and then they do something very interesting here. So let me turn these into hex, and I'm going to show you guys something cool. So those values actually mean something, especially when you're dealing with import address tables. I'll show you guys that in a second. They're also, it looks like they take that hash 1, the first transform, it looks like they and it to get the lower word here with an extra 1 on it. They set that value to 1, but if you ignore the 1 part there, you can see that what they're really doing is they're masking out the upper word of that D word. So they're only keeping the bottom word. And I saw as well, where did I see this? I saw they're actually doing this again. So there's an and here where they mask out. Oh, yeah, okay. All right, so let me add some comments in here and I'll explain what's happening. So here, we're going to name that var API word, API hash word. It's the lower word. and they are comparing that against whatever is coming back from this function call with another mask. So this is definitely, they're definitely using the bottom part of that API hash to do a comparison here. And so that makes me think, and if you look up here how they build the transform number 2, they actually do a shift right 21. So that will actually use the upper word of that D word. So if you think about the transform hash here, that's actually a D word. So there's 2 words together. They're using the upper word for the second transform. So they basically shift it over so it's there. And then for the comparison, they null out the upper word and they keep the lower word to do the comparison. So let's look at the lower word first, because I can see a comparison here, so it's probably going to be easy to figure out what they're doing. They have to be doing something in this function in order to compare it. So we kind of want to zero in on here and reverse engineer what's going on in this function. But remember I said that these 2 values mean something to me? Let me show you something that's kind of interesting. Now again, this just comes from reverse engineering a lot of malware that does dynamic import address table resolving. But whenever you see like the 3C78, and they're actually being, so this actually is an offset. It looks like they're calculating an offset because they're casting it as a D word after they add that on, and then they're casting the result of that as a D word as well. So what this means is what this looks like a pointer that's moving down a bunch of memory whenever you see something like this where there's a cast and a cast. And so let me show you the Corkami PE header. So this is I've referenced this in other videos. This is the Corkami PE101 Windows executable, or 102 PE102 Windows executable format drawn out in visual form. So this is what a PE file looks like. This is all the different offsets and what they mean. I'll link this into the video description below as well. Super handy to have around. So if you look at, this is the DOS header. So this is the thing that says like there's an MZ here, and then it's like this program cannot run in DOS mode, blah, blah, blah. And then there's the PE here, which is where the PE header starts. So a PE file has the DOS header, the PE header, and at 3C, the offset 3C, is where the pointer to the PE section exists. So if you were to go to the very beginning of a PE file and you went to the offset 3C, that would be a pointer to where the beginning of the PE file is. And so if we look at our IDA here, you can see that 3C. Now 3C by itself, I mean, it could be just some random value, but coupled with 78, hex 78, let me show you what that is. So anytime you see this 3C78 and its offset pointers, you're looking at one thing here. So let's start at the beginning of our PE header here, and we'll go down to 78. So here's offset 70 plus 8 gives us the export table. So anytime you see an offset 3C added to offset 78, almost certainly, especially if you're dealing with dynamic imports, they are walking from the very beginning of a PE file to the export table. Now you might ask, why? Why walk to the export table? Why do they care about that? Well, the export table has, if we follow this line here, the export table has all of the names of the exports. So if you have, like, say, kernel32.dll, all of the functions for kernel32.dll are in the export table. And it also has the addresses of all of those functions. So if you were going to dynamically resolve some imports, you would definitely need to be looking at the exports table. So that's definitely what it looks like to me. And I'm going to link a very good article. It's actually one of the ways that I learned about reverse engineering malware. There's this old blog called Dr. Foo's blog, and he goes through all these different steps of different techniques you can use for reverse engineering malware. So let's pull it up here. So he has this awesome article on the export table. And so I'll link that. He talks about what I just showed you here in much more detail. And he also has a nice copy of the export table function here, the struct here. So I'm going to show you something kind of cool with IDA. So we can actually copy that struct here. I just right click, copy it, go back to IDA, and we can actually apply that in IDA, and IDA will automatically populate the variable names for us. So that's going to help a little bit with our reverse engineering. So let's pop back here. We're going to go to View, Subviews, Locals, and right click, Insert, paste that in. And this is a definition for a struct. Now, if you guys have never seen this before, definitely go check out our reverse engineering C++ tutorial video. It was like a month ago or so when it came out. I'll link that in the description below. That explains how all this works and what this means. But basically, we're going to create this struct, and then we're going to go back to our IDA view here, and we can right click on our variable here and turn it into the export directory struct. And you can see that they've automatically labeled these with the variables. And of course, this is exactly what we'd expect to see. So we'd exactly expect to see the export table names and the address of the functions being used in here. So let's copy these variable names over so that we can continue our reverse engineering here. So we'll name var underscore. All right, so now that we have that labeled, let's take a closer look at this function down here. So you have the address where the export names are. So these are things like create process, reg key, blah, 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 all those different function names. And they're each one, it's an address of the name. So it's going to be 4 bytes. So that's why they're adding 4. And it's in a while loop. So it looks like each time they go through this while loop, they grab a new address, they pass it to this function. Then they AND that function to get the lower word, and they compare it against the API hash lower word. So without having to look at this code in this function and figure out what it does, I'm already almost certain that it is creating a hash value out of the export name, the API name, so that it can then be compared with the hash value that is stored in the PE file, hard-coded to actually resolve those imports. So like I showed you before here, all these values. So they're actually taking the lower word, so the lower 4 bytes, they're using that as the hash value to resolve the name. Now, if I was a betting man, if I had to guess, I would guess the upper 4 are being used to figure out which library it comes from, so the DLL name. They're probably using the top 4 for the DLL name because we know they're using the bottom 4 for the actual function name. That's just a guess, but I've seen enough of these that's what I think's going on here. So let's take a look at how this actually works with this hash value. So let's jump into this function here. Okay. So a little bit more fun. So anytime you see some crazy stuff like this where IDA is doing a jump out to a location, what that means is the Hexphrase decompiler has probably thrown some sort of error. And what it wants you to do is it wants you to look at this. Basically, you can double click on it and it takes you to another function. But really what this means to me is look at this in the disassembly view and try and figure out why the decompiler didn't work. So I'm just going to grab this function here and I'm going to look at it in the disassembly view. So I'm going to press G to go to that address, and I'm going to right click and do a text view. So here is our function, and what we're doing is we are jumping to this address down here. Interesting. And then what do we do after that? We have a move, continue on, test, jump back up here. So it looks like this is a whole one big function, but the decompiler has messed up and created a whole bunch of different functions. So that's not a big deal. We can fix that. Let's just go and undo all this stuff. So I'm just going to highlight this, press U to undo it. I want to undo this as well. Okay, and so we're going to come in here, press P, and hopefully it looks like it's turned. Okay, so it looks like it's turned it all into one big function now. So now we should be able to press F5. There we go. So anytime you see this, usually what happens is when the decompiler is running, it's trying to identify different functions and decompile them. Some of the ways that they identify functions might be wrong, might be incorrect. And so what they did there was they basically split this one function into 3. So it didn't look very good. So what I did was I undefined all that and just redefined it as one single function. So now that we have a nice decompiled view that we can look at, Let's press X for XRES, jump back to our function here. So I think what I'm going to do is I'm going to name it malware underscore API function resolve. Because it's actually resolving the function, I believe. All right, so let's take a look at this function. Remember, it's being passed the name of the function, and it's going to be creating most likely a hash to compare against the hash that's hard-coded. Let's jump in here. We know that arg0 is arg function name, because it's actually the name is being passed in, so that'll be a string. What do they do with this string? They assign it to var1, which is int 8. So int 8 is actually a char. It's a single character. What is almost certainly happening here, if we take a look at the disassembly, is they are using the lower register, or the least significant byte of the ECX register. So see, EDX has, so this is where the function name is. It's moved into EDX, and then EDX, the data where that address points is being moved into CL as a byte, and the decompiler doesn't really like that too much. We could just look at the algorithm here. It's pretty simple. It looks like they are moving 2B into EAX, so that's pushing and popping into EAX. They're moving a byte of the string, the function name, into CL. They test to see whether it's null, so that would be the end of the string. If it's null, they return. If it's not null, they multiply 0xf times EAX, which is 2B, and then they increment EDX by 1, so that is the pointer in the string, so they go to the next byte, but they're not quite done with the actual byte that they copied, so the first byte of the string is then moved into ECX, and ECX is added to EAX. So if we look at our pseudocode here, it's actually this algorithm, but instead of V3, that should definitely be V1. So what we can do is we can kind of recreate this in Python. If we open up I like to use Sublime Text. It's just a free editor. So what I'd like to do is I'd like to say the function name equals, and we'll just give it a placeholder for now, something like create process, and then we're going to have a loop through that string. So for C in function name, and we need an output as well, I think. But the output, they called it return here, or result, so let's call it result equals, and they start it with 0x2b, and then what do? They say result equals the ord. So ord is just casting the character C as an integer so that I can actually use it in some math. So they do the ord plus 0x1f, or OF, and times the result. And that's about it. Probably want to move this up here. So that's where it's starting out. And let's print out that result. Okay, so that looks like that's our function to create the API hash. So let's actually just create this as a function. We'll do def get API function, and we'll call this function name. Let's just tab all this stuff in here. All right, so that's good for now. Let's go back here, and they also and the result with that. So let's pop back over here and it. Okay, and they compare that against the hash that we saw in the table, but they take they and that, but they also do this little transform on it here. So let's copy this little transform out, let's copy that out, and we'll recreate that in Python as well. So let's say def transform hash, and this will be the API hash. And what do we want to do here? We want to result equals, we don't need this stuff here. So they XOR it just removing the casts here. So they XOR it here, they shift left 16, do another XOR. Did we miss a bracket at the end here after 16? Or are we missing a bracket? No, I think we're good. And then they return the result. And that result is ANDed with 0x1, 1, 2, 3, 4, 5. Is that right? Is it only 4? Let's see here. 5. Oh, so it isn't the lower word. It's a little bit more than the lower word. Ah, interesting enough. Looks good to me. Okay, so now that we have that code, we should probably test it out here and see what's going on. So let's go back and find that table again. So we'll find where this was called from here. Here's the table. So we'll grab that first function in the table here. Let's grab that byte out. Let's save that in our here as a API hash. And then we probably want to open up a debugger, and we want to see what that first function actually resolves to, and we'll test it out and see if this works. So let's pop over to using debugger here, right? So we'll pop up in our debugger here, copy our sample over, run until we get to the entry point. And remember, the import address table happens in the first call. So let's step into the first call. Here's where we think that we're resolving the APIs, where we just reverse engineered. And you can see that that must happen because the next call here is to one of those hashes in the import address table. So that must be resolved before it can be called. So let's step over that function. It's actually been resolved to an API. So what we can do now is we can then follow this function here in our dump, follow and dump. And we can't really see what's going on here, so let's right click and we'll change this to be addresses. And let's look at our first address here is wsprintfw. So that is the API name that should be resolved here. So this should be the very first function in the import address table. So let's test that out here. So this should be wsprintfw. And let's open up a command shell here, Python, and test this out. So let's copy in our functions here. Copy in this function as well. All right, and here's our API hash, and here is our function name. Okay, and so let's call getAPI function with the function name. So, and that's going to return a value. So let's print that value in hex. All right, and then let's call hex of transform hash, and we'll pass it the API hash. Oh, whoops, a little typo here. That should be API hash, not our API hash. Copy, paste. Always a couple errors when you're typing Python live. Let's go back here.
Hell no, to the no, no, no. Yeah, to the no, hell to the no, to the no, no, no.
Super close here, but it looks like there's a little difference here, 3 versus 1. Let me see if I copied that name correctly. So let's pop in here. I think that's a capital W on the end and not a lowercase. So let's pop over. I think I used all lowercase. So let's pop back here and we'll try. Let's look here. Yeah, they're all lowercase. Let's try capital W on the end here. Paste that in here, and there we go. Okay, so small mistake there copying. The capitals kind of look the same as lowercase for W's. Go figure. So anyway, we now have our function here, and we can basically use this to compare function names with the hashes that are in that table. And I think that's where we're going to stop for today, because the next step would involve turning this into an IDA script and then using it to automatically generate the function names for all those hashes. But that involves a little bit of IDA scripting. So I'm going to save that for a separate video. But this has been our first sort of step into reverse engineering malware past the unpacking stage. And like I said, with a lot of malware, reverse engineering the dynamic imports and building a small script like this in order to reverse engineer that algorithm is pretty much the first step that you're going to need to do if you want to reverse engineer the malware. So I know this was a little bit longer and possibly a bit more boring than some of our unpacking stuff, but hopefully those of you who have been asking for more actual reverse engineering how-tos enjoy this. Let me know in the comments below if you're interested in seeing more of this stuff or more of the sort of tricks that we use for speeding up unpacking and stuff like that. I enjoy doing this as well. This is what I do for a living, so I think it's kind of neat to sort of pass on some of these tricks, but it's up to you guys. Let me know what you think. So like I said, I think the next video we're going to talk about turning this into an IDA script and using it to automatically populate the function names. So until next time, keep exposing the mechanics behind the malware. Stay curious.